Good morning everybody. We are back with rate processes, and we were discussing reaction dynamics, and we were in the last lecture here this scattering process. So, in the last lecture we ended stopped our discussion with this calculating the differential cross section, that is d sigma d omega, okay, and from that we arrived at the expression d sigma d omega, which is I theta which is sum over b sin theta into d theta dB, and we have got two situations. One is if sin theta equals 0, the other is if this is equal to 0. Okay, so two singularities. So, singularities, that is I theta tends to infinity. If theta is equal to 0, case 1, if theta is equal to 0 means sin theta is equal to 0, which is called the glory singularity. Glory singularity. And number 2, the other one, if d theta dB is equal to 0, that is called the rainbow singularity. Okay. So, if we plot this d sigma d omega with theta, then this is the situation, b by sin theta d theta dB. Okay. So, this corresponds to glory singularity, and this corresponds to, see, it goes to infinity, a very high value. Again, it is okay, and this one, you see, this becomes asymptotic, which is called the rainbow scattering, rainbow singularity. Okay. So, therefore let us try to see what is this. Now, what is meant by, so definitely from the mathematical perspective, this becomes this one is very, this one becomes differential cross section becomes very high under these two situations. Okay. Now, what is this rainbows, rainbow singularity, that at this situation d theta dB is 0. Classically, we obtain a discontinuity in the differential cross section, okay, as it is here, differential cross section. Okay. Now, differential cross section at cross section at theta r, rainbow angle. Okay. Now, for theta less than theta r, theta less than theta, I mean when theta is equal to theta r, we obtain this situation. So, we obtain the singularity. Now, for theta less than theta, 3 values of B can lead to deflection through the same scattering angle and leads to interference. It is again a case of interference, I mean which is called the supernumerary rainbow. Okay. Now, the features in basically the features in d sigma d omega are directly related to the nature of the potential energy curve. It is very much related to the nature of the potential energy curve, and also this theta r, that is the rainbow angle, the well depth theta r is sensitive to well depth as well. So, this is very important, that it depends on the well depth also, I mean the well means this potential well depth. Okay. So, these are the two I mean one is glory, another is rainbow. These are the two situations on this d sigma d omega, and the physical significance for this rainbow is that that we obtain this rainbow when this d theta dB becomes 0. Okay. So, if you want to know in more details, you can consult this textbook by Raphael de Levine. Now, let's one important point that this, as I told you, that supernumerary rainbow, that is for theta less than theta r, that is the less than theta r means rainbow angle, 3 values, I mean 3 values of B will lead to deflection to the same scattering angle. So, that will, as I told you, that d sigma d omega is very much related to the nature of the potential energy surface. So, supernumerary rainbow gives us information about the nature, I mean about the range and shape of the potential near the minima. Okay, these informations can be obtained from this supernumerary rainbow when 3 values of B corresponds to same scattering angle, which is called the supernumerary rainbow, and leads to interference when interference known as that is for 3 values of B leads to supernumerary rainbow. So, this rainbow is very important in knowing the nature and depth, I mean near the minima. Okay. Now, next so we talked about we have been talking about this elastic scattering. Now, let us think of inelastic scattering. Inelastic scattering, okay, where translational energy is converted, I mean transferred to rotational, vibrational, internal motion, but without any rearrangement of the atomic framework, Example, say translation to vibration, T to V, okay. Say if it is inelastic scattering, then maybe argon plus carbon monoxide in V equal to 0, it collides, argon plus vibrationally excited carbon monoxide. So, the translation energy of argon is given to the vibrational mode, and argon is gets its energy reduced. Example for vibration to vibration. Vibration to vibration. V to V, say nitrogen V equal to 0 plus carbon monoxide V equal to 1, giving rise to nitrogen V equal to 1 plus carbon monoxide V equal to 0. Okay. So, it is basically energy interchange. So, one, I mean basically you have got say so these are the say two vibrational levels, say this is for say nitrogen and say this is for carbon monoxide. So, these are vibrational levels. So, 0 1 0 1. So, because of collision this energy is given, maybe this excess energy is given to here, thereby it is coming down to here. Okay, so exchange of this is basically the vibration to vibration energy transfer. You can find plenty of literature on this aspect. Okay, even it is by scattering. Okay, maybe you can think like when a photon collides with an atom, then energy of the atom increases. So, you may think in that way, I mean classically you can think that this energy, this photonic energy is transferred, and thereby thereby your electronic energy is increased. Although classically it is difficult to explain this phenomena fully, but maybe classically you can start to defend in this manner. Okay. Now, so there are factors, whether there is energy mismatch. I mean, vibration to vibration is important when there is less mismatch between this and that. If it is highly mismatched, then there is a problem. If they are very close, then easily energy can be transferred. So, there are several aspects, I mean several factors which determine whether this energy transfer, vibration to vibration or translation to vibration, translation to rotation, these are feasible or not. Okay. So, controlling factor, one is, think of a low efficiency process. So, low efficiency process, efficiency case has, for example, translation to vibration. Okay. The cross section, this transfer efficiency. So, cross section will be small, cross section small, and generally it involves when B factor is small, impact parameter is small. So, usually involves small b, involves small b, and it is controlled by short range repulsion. Repulsive interaction. Okay. High efficiency case, maybe translation to rotation, or maybe vibration to vibration resonant. Okay. Cross section, high, large, and usually involves a large range of B. Range for B, and it is controlled by long range attraction. Long range attraction forces like dipolar interaction. Okay, so controlling factors for this energy transfer, and it depends on like if it is a low efficiency case, then short range repulsive interaction. If it is a high efficiency case, so long range attractive forces like dipole interaction is responsible. So let us look into scattering experiment again. Okay. Scattering experiment again. So a crossed molecular beam, say for example lithium ions plus H2. So vibrational level equal to 0, rotational level say J is equal to 0, 1. These are populated. Okay. So crossed beam interaction like this, crossed beam interaction. Okay, giving rise to lithium plus H2, of course B primed, J primed, some different V and different J. Okay. In this case, since energy is transferred from here to here, like so of course the velocity of lithium plus should be altered because of this energy transfer. So how to look into that? Okay. So now in this case the energy has been transferred, means and of course V becomes V primed, J becomes J primed. So it is a case of inelastic scattering. So how to look into that? So if you can detect Li plus, okay, means its velocity, okay, if you can plot the contour of velocity, okay, in different direction, then you should be able to get some idea, okay, and that can be done by time of flight mass spectrometry, TOF-MS, time of flight mass spectrometry. In that case, you do the mass spectrometry and of course monitoring the time of flight. That is, suppose you have got lithium ion over here and you have got say same lithium ion over here. So by knowing how much time it takes to travel from here to here, you can get idea, means you can find out the velocity. So you detect the lithium over here, you detect lithium plus over here. Okay. So using time of flight spectrometry, mass spectrometry. Okay. Now, when it is the case of scattering, there is a provision for head on collision and there is a provision for like sideway the colliding, I mean say B molecule can go like this. So, you have got like H2 over here, H2 over here, although it is a diatomic, but here we are showing as a just as a ball. Okay. Lithium plus is coming this way. So, what is going to happen that when it directly hits almost head on, it will rebound, I mean backward scattering, back scattering, back scattered. Okay. So, in this case theta will be greater than 90. Okay. But maybe other situation that forward scattering may take place like this. So, forward scattering, in this case theta will be less than 90. Okay. Theta will be less than 90 degree. Okay. These are the two situations then that you can think of, that may be possible, two extreme situations. Okay. For forward case, forward scattering, so kinetic energy loss will be less for lithium plus. So, small loss in kinetic energy of lithium plus, and that corresponds to excitation of H2, V equal to 0, J is equal to 1, 2, maybe V is equal to 0 to maybe J is equal to 3, and it has got large cross section. And the second situation, that loss in kinetic energy is more for the back scattered. So, loss in Ke more for back scattered. Okay. And that corresponds to excitation, since it is more loss, that corresponds to excitation from V is equal to 0 to maybe V prime is equal to 1, 2, 3. So, V is equal to 0 and say J is equal to 1, 2, V is equal to 1, 2, 3 and J primed, and its cross section less. So, these are the two situations that we can think of. Okay. So, definitely back scattering will have lower cross section than the forward scattering. Okay. Because you see probability wise two body collision means head on collision, out of many situations side and side on or sidewise or whatever, this situation is perhaps will be lesser in cross section. Now, so since there are two options, one is this, another like this, so two extreme situations. So there is a there will be angular distribution in various angles. Okay, so angular distribution you can measure. Okay, like here, cross molecular beam experiment. Okay. Now, what is done in molecular beam scattering experiment? It is like that one of the molecular beams is usually chopped. I mean, there are two molecular beams, chopped or pulsed. Pulsed means not continuous, but say on then off, on off like that. So in that case, that will help in doing this time of flight spectral mass spectral measurement. Okay. So in doing the time of flight mass spectrometry, out of two beams, one beam can be pulsed. I mean, in between two successive pulses you can measure the time of flight, or maybe on beam is on, then keep it off for the time of flight measurement of say lithium plus. Okay, and then again keep it on, I mean make it on. Okay, so how to detect, I mean these scattered entities? So one may be ionization detector. Ionization detector, that is hot wire ionization. Okay. So, like what is done is you have got hot ion, I mean hot wire, and then when the element or something like M or E, the element, and or maybe its compound say EX, when hits, then maybe ionization takes place. Okay. So maybe M or MX ions. Okay. Then this ion generates some current. This way you can measure using hot wire ionization, but it has got, this is having good angular resolution, but energy resolution wise it is not that great. Okay. Another is electron impact ionization coupled with mass spectrometry. Okay. So it is electron impact ionization coupled with ionization plus mass spectrometry. And this is a universal method of detection. Okay. So this is another method, and the thing is that rarely it has sensitive to allow product quantum state resolution. So product quantum state means, say in one case say it is in vibrationally excited another one may be vibrationally not excited or little less excited, like one is say V is equal to 2, another is say V is equal to 5. So, it is difficult to resolve these quantum states. Okay. For example, say F plus H2 giving rise to HF plus H. So, this problem is there, that is its limitation. And for the earlier one, this speed resolution wise, this one, the hot wire ionization is not that great, and but here quantum state resolution is not possible. What about other methods? There can be, of course, spectroscopic method, okay, like laser ionization method or laser induced fluorescence method. Okay, that suppose your species is fluorescing, or maybe the moment your reaction product is directed to a direction, then you shine your reaction mixture with laser, then it will say out of many one of the components in the mixture is giving rise to fluorescence. So, you can measure it. So, spectroscopic method is always sensitive and accurate. So, therefore, using laser induced fluorescence or maybe laser ionization method, you can do it, but it has high energy resolution, sensitive in the sense that if the population of your species that fluoresce, if it is significant, then it may be sensitive, but if it is very less, then sometime it may means detector may not be able to detect the fluorescence or maybe the ionized things, ionized entities. So, and various other detectors are possible, means little variation of these basic things. Okay. So, you have to do the time of flight mass spectrometry while doing this molecular beam to look into their velocity distribution, I mean velocity contour, and then you should be able to know whether it is a case of backscattering or it is a case of forward scattering. Next is we will move on to mechanism of the various such processes we have been discussing. So, one is harpoon mechanism. Okay. So, harpoon mechanism. Harpoon mechanism. Example: K plus I2 giving rise to Ki plus I. Now, let us plot the data in the form of contour plot in the center of mass system for such that center of mass is stationary for such a system. Okay. So, this is your K, this is your center of mass, something like this contour. Okay. this side is 0 degree, this side is 180 degree, and you have a circle, although it is not circle, you have to draw a circle, and this side is 180 degree. Okay. You see that contour, this is your center of mass, product distribution is in this side. Okay. So, in the 0 degree, this side, not in the back scattered side. Okay. That this contour represents lines of equal product flux as a function of Ki velocity. We are looking into the velocity of Ki. Okay. Velocity of Ki. Okay. So, it is a contour plot in the center of mass system such that the center of mass is stationary. So, this contour represents lines of equal flux of product, lines of equal flux, that is equal flux lines are joined, equal flux of product in terms of Ki velocity, potassium iodide velocity. Okay. And the circle outside represent, this circle outside represent the maximum possible product velocity, which is set by the energy conservation. Okay. So, it is basically this is your center of mass, and center of mass is thought to be stationary. I, this is K, and your Ki. So, you are detecting Ki velocity with theta. Okay. So, lines of equal flux of product is drawn as a function of Ki velocity. Okay. And in this case, scattering in the forward sense, we are getting. Okay. Now, when it is the case of rebound, now the case of rebound happens when hitting head on. Okay. And in that case, it is strongly backscattering. Now, what is the harpoon mechanism? Now, what is the meaning of this harpoon mechanism? Now, for fairly heavy or heavier reactants, what is happening that since it is a case of forward scattering, so you have got your iodine over here, like your K is coming maybe this way. So, the moment it is coming close to this iodine, this iodine, it plucks it, that is, it takes away and then follows this path. Okay. So, it plucks the light atom. Okay. It plucks the light atom from the other reactant, or maybe plucks one atom from the other reactant as it passes. Okay. And newly formed diatom is forward scattered. So, newly formed diatom means this Ki is forward scattered, and the other reactant, that is the reactant that is acting as a spectator, this cannot do anything as it. So, it remains over there. Okay. Only thing is that what is happening to it is that there is a loss of atom. Okay. So, it is basically a spectator that as if it is helpless, it cannot do anything. Okay. So, it comes this way, then it plucks this iodine, becomes Ki and goes away. Okay. So, this is pretty much what is meant by your harpoon mechanism. It is a harpooning process. Okay. And since it is forward scattered, so that is why you get this contour in the forward direction, not in the backward side. Okay. So what is then what can you talk about this harpoon mechanism? It has got large cross section for the reaction, okay, like many other alkaline halogen reactions. It gives you forward scattered product like this. Okay, this is the characteristics. Low energy release into translation. Okay. So, translation energy is not that much. So, Ki is in highly excited, internally excited, okay, not much velocity, low energy release into translation. Okay. So, the formed Ki should be internally excited. Now, this electron transfer harpooning takes place under the condition let us try to look into. So, electron transfer harpooning. This takes place under the situation that let us look into the potential energy diagram. Okay. Say for a reaction that K plus Br2. Okay. So, giving rise to say Kbr plus Br. So, thing is okay. So, this is your covalent surface and this is ionic surface. Okay. Ionic surface means it is K plus Br2 minus. Covalent surface it is K plus Br2. So, what is this gap? This gap is means there is a gap in energy. Okay. So, we will look into it. So, V covalent, okay, and this is your RC, there is crossing point. Okay. V covalent RC is V ionic at RC, which is almost equal to 0. That is, this means IK, ionization energy of K, minus EA, electron affinity of Br2, is equal to E square by 4 pi epsilon 0 RC. Okay. So, that is delta E, this is your delta E. Okay. Okay. Now, in this case RC is of the order of 6 angstrom. Okay. Means further from your this true ionic potential energy curve minimum. Okay. And how to estimate the cross section. So, cross section under this condition, let us try to find out the cross section and also assume Pb equal to 1. So, your sigma is equal to integration from 0 to B max, okay, which is equal to RC. Okay. So, impact parameter RC twice pi B dB, which is equal to pi RC square, is of the order of 100 angstrom square. Okay. So, what is happening here, that Br2 minus is formed with internuclear separation such that there is a little repulsion between Br and Br minus, okay, and K plus carries off Br minus in its original direction, that is the forward direction. Okay. So, Br minus is formed with internuclear separation such that there is little repulsion between Br and Br minus, that is Br and Br minus. Okay. Br minus. So, they are at such an internuclear separation that there is barely a repulsion, and K plus carries off this Br minus, I mean it takes off, because they are nearly, I mean they are not repelling each other. Okay. Electron transfer making Br2 minus, and then there is basically they are at such a separation that there is no repulsion between them. So, they are loosely, as if loosely bound, and K plus takes off that Br minus and goes away, making K Br. Okay. So, that's an interesting situation for electron transfer harpoon mechanism like happens for many other alkali and halogen reaction. Okay. Next, rebound. What is this rebound? Think of a reaction like K plus CH3 I giving rise to Ki plus CH3, that is the product is rebounding. I mean it is not forward scattered, but it is back scattered. It takes off and then comes back. So, this is your species, I mean say CH3I, K reacts and then goes back. So, in center of mass system you can represent Cm, okay. You can represent this, and this is your scattered Ki, theta is more, okay. This is your CH3I, this is your K, okay. And if you do a contour plot, then you will be seeing this, say this is your Cm, say stationary Cm, from this side your K is coming, okay. So, your contour plot will be something like this, like this. So, it is mostly this side. So, if you detect Ki, then this will be mostly in this side. So, it is back scattered product, I mean rebound, okay. So, that means your product gets rebound this way as per this figure. Therefore, this side your contour, contour shows that the probability is more over here. So, and it has got a small cross section. Backward scattering, it is that happens with small impact parameter B, and it releases high translation energy. That means, in contrast to harpoon, where low release of translation energy and excited, highly excited, here but here the situation is opposite. It is also a harpoon reaction, but electron affinity has got a change in sign. I mean electron affinity, I mean it acts in the reverse. I mean EA of CH3I, this one is negative, okay. In contrast to your electron transfer harpooning, okay. So this case is also, this rebound case is also a harpoon reaction, okay. Okay, so I guess I should stop over here and I will just quickly have a recap. What we have done in this piece of lecture, we talked about this singularities for differential I mean cross section, okay. So differential cross section, and then we talked about this rainbows. Then we started with inelastic scattering. Then we discussed this this harpoon mechanism. It is basically a plucking mechanism. So we discussed I mean for harpoon mechanism, you can have forward scattered as well as back scattered, as I talked in terms of rebound. So I guess that's all for today. So in the next piece of lecture, we will again talk about this means a little more on this harpoon mechanism, and little more on this harpoon mechanism. So that will be taken up in the next class, and after that maybe some other aspects of the observations, I mean some other aspects of chemical reaction dynamics we will take up in the next pieces of lectures. So till then, thank you.